Good morning, good afternoon, everyone. We still wait one more minute before we will start the PrecisionTox webinar. In the meantime, I'm putting the agenda. Do you see the agenda? Yes. You see myself next to the agenda? Okay. All right. People are slowly coming in. So let me start with the welcoming words from Alter Talks. So today we have 214 registrants for this webinar. My name is François Busquet. I am the CEO of Alter Talks. It's a science to policy company. We are also the work package leader for the dissemination of this European research project, PrecisionTox, and I will be your host this afternoon. As it was mentioned in the invitation, this webinar will explore how Omics bioactivity data can be used to increase confidence in chemical grouping. It will include both regulatory and industry perspective, highlighting the importance of grouping to support Red Cross and to enable a reduction in animal testing. Today, we have a great lineup of speakers, as you can see, that will present the progress in the application of omics data for chemical grouping to support Red Cross. The presentation will be followed by a dedicated Q&A session. Please put your question in the Q&A box and indicate to whom they are directed. Please note that the colleague from ECHA, Thomas Obansky, will leave soon after his talk, so we will collect the question right after his lecture. This webinar is recorded, as you noticed, and it will be uploaded to the PrecisionTox website in due time. We'll start today with our first speaker, which is Francesca Trivelloni. So she will introduce the industry perspective on using grouping for chemical safety assessment. Francesca is a product stewardship manager at CEFIC, the European Chemical Industry Council, serving in her role as a permanent observer in ECHA Endocrine Disruptor Expert Group and as a member of the CTAC EDTRS Steering Committee from 2025 to 2027. She holds a master's degree in regulatory toxicology at the University of Milano and conducted her research at the CNRS in Paris on endocrine disruptor, particularly dedicated to phthalate exposure. Francesca, I stop sharing and the floor is yours.
Thank you very much, Francois. Meanwhile, I'm trying to share the screen, and good afternoon or good morning, everyone, from my side as well. Very glad to be here today and present you, as it was just mentioned, some of the most updated discussion regarding grouping that took place in CEFIC. So I hope you can all see my screen. Otherwise, just say, okay, yeah, I can see a few hands saying yes, so I will continue. And let's give it a start by giving you this short overview of the presentation for today, which is actually the reflection of the different steps that we took in our work, in our internal discussion, as I said. So we started, and we will start with a short analysis on the current state of the use of the grouping. Afterwards, some reflections and the identification of key elements that for us were considered as potential solution to fulfill some of the existing gaps identified. And then afterwards, some consideration on why we think that this could be beneficial, not only for the chemical industry, but for all of us and all of you that are here today. So yeah, before even starting, this is a disclaimer for you to look at and maybe to train your minds, but it's really where we have been starting with our work. So thinking about grouping and how we wanted it to be defined. And we had identified the grouping in our work as this overarching concept and fundamental concept in the chemical assessment space, regardless of any other assumption that we can normally use him for or generally thinking about. So as I said, we started by asking ourselves what were the issues that we have seen and we currently see in on the use of the grouping. So beside the issues, of course, we have identified some positive sides. You see them here, the pros, and we all are here aware why grouping is such a strategic and useful tools. But along with them, there comes also some cons, some let's say challenges, and definitely for us, we have been seeing that together with the grouping, it also comes a certain degree of uncertainties for the analysis that we want to take and carried out, but also on what it concerns the interpretation of the data that comes out of the grouping approach. And this refers to the fact that it also transposed into the regulatory acceptance of this grouping. So in many situations, you might have the result that is coming from the industry that can be questioned on the authority, or there might be other vice versa, some situation where the industry have challenges in interpreting what it comes out of the other side. And possibly even since today we have also the academia, we can also have some certain degrees of discrepancy even in this other case. So as I said, after having done this sort of initial analysis, we wanted to go back to the roots of the grouping. So I think that the very early stage, we start talking about grouping when we want to define an hypothesis. And so we saw that starting from the hypothesis, trying to bring back some fundamental scientific principles that could have been our potential way forward. And so we have identified this so-called 10 science-based principle that you see here on the slide as potential key elements that are needed to better define the strategy at the very early stage and having more consistency in the principle to be applied. So you probably, if you scroll down to the list, you see it's nothing really new. Many of these principles already exist in other guidelines that are available for grouping. But what is actually new for us is the way of rethinking about them. And so a way to restructure all this scattered information and criteria to be used for the grouping in a way where we can build an overarching science-based framework. And we have identified that this opportunity of having this regulatory agnostic framework as a very early step. So our step one in the grouping strategy should be built upon the 10 guiding principle, and then afterwards, subsequently, starting with a second step on a more regulatory based and let's say focus to consider further the hypothesis into the regulatory application. After that, of course, this is the idea, but then why we think that this could be beneficial for us, but also for all of you. And the reason why I'm actually here today, it's because we really think that by improving the use of grouping in a way where we can harmonize the principle, not only from the industry perspective, but from all the actors that wants to use the grouping, we can encourage to have a wider acceptance. We can lower certainly the uncertainties that comes along the grouping, but we can also open some doors for new type of data, new methodologies, promoting their use from the very early stage, where we can, from a scientific perspective, describe them with all the uncertainties that comes along them, and trying to define the boundaries of the limitation, but also on the strengths of integrating these lines of evidence. So to bridge with what will come next to me and the other speakers that will focus even more on the NAMS perspective and the omics specifically, this is just to mention that Cefic has also worked via the Cefic LRI program, so our long-range research initiative on this specific project, and I wanted to mention it because I think it's kind of a nice bridge with what we will discuss later today, but it's also an opportunity to show a practical example of how the NAMs can be applicable into the grouping space. And certainly there are few of relevant points here outlaid, but I think that some people after me will deep dive into the details. So I'll just gonna go directly into my take-home messages for today. I think that it's very important for us to reflect about the crucial entity of an hypothesis while we build upon the grouping strategies. And for that, it's very important that this hypothesis is built on scientific arguments. And these scientific arguments, we call them principle. We really think that needs to be independent from the regulatory context. So we should think about our hypothesis as a let's say a upfront step where it comes along and as a unique consideration, and afterwards we refine the context of the use. And finally, the grouping can efficiently reduce animal testing. We will see even afterwards with the other speakers. So to gain this acceptance, we really need to make as a foundation the scientific arguments of the use of this data, and in order to build the trust and promoting their use after their acceptance into the regulatory space as well. So very last take-home message, I think the most important one. I think this was for us an attempt to start this dialogue with all of you. So not only from the industry side, but also regulators and academia. We have to work together in order to find a solution on the issues that we see and that we know that still exist on the grouping. We think that this could be a glimpse to start rethinking a little bit what already exists and build upon on that. And we need your help, of course, to make it a success and potentially a solution for us all. So with that, I thank you all, and happy to take any question afterwards and let the other speakers to continue the discussion.
Thank you so much, Francesca. Now, we will have time for questions at the end of this webinar, as I mentioned. Introducing our next speaker, Tomasz Zobanski. He will present the regulatory perspective and the potential role for omics in grouping. Thomas' background is in biophysics and computer science. He graduated at, and I'm pronouncing the best way I can, Wrocław. Oh my God. University of Technology with a PhD in technical physics. I trained on that one. Since 2009, Tomasz works at ECHA, where he's currently a team leader in ECHA's alternative test method unit or method team, focusing on the development and application of the alternative method in various regulatory process. As I mentioned at the beginning, Thomas will take questions right after his presentation as he must move to another meeting soon. So please put your question for Thomas in the chat during his presentation. Thomas?
Yes, thank you very much for the great introduction and taking the effort to pronounce Wrocław well. Thank you. Okay, I think you should be able to see my screen is coming. Can you see it already? Yes, great. Okay, let me start. Yes, so good afternoon and good morning, everyone. This is Tomasz Sobański speaking. So I've been asked by organizer to set the scene and share briefly the regulatory perspective, why we believe grouping is an important grouping and read across is an important tool for regulatory application, and why we believe omics has really great role to play there. So let's start from the beginning. I think in 2020, ECHA published its integrated regulatory strategy, when basically we realized that regulating substance by substance does not have much sense because many substitutions are very similar to those which are of hazardous properties, and sometimes they have even more hazardous than those which have been already targeted. So we started to try to address chemicals of concern in groups. And this work is still ongoing until till now. But not only we've been quite keen on doing grouping and applying grouping in regulatory process, our registrants, especially REACH registrants, feel the same, because if you look at the statistics on what kind of options registrant use to fulfill the information requirements in the REACH registrations, you will see that actually read across is the most popular adaptation among all other adaptations, and it's basically very popular way of fulfilling information requirement, almost as popular as submitting experimental data. So we could see that also our registrants are convinced that read across is a great and sometimes grouping is a great approach towards fulfilling information requirements and trying to identify the hazard. Of course, problem is that majority of those adaptations, especially at the beginning of REACH, were not so well done. So basically, we had to reject a vast majority of those adaptations. This is getting better with time, and I think as well, thanks to the CEFIC efforts, I think we are getting better and better read across justifications. But in general, we've collected from our colleagues which are evaluating those most frequent deficiencies is mainly missing read across hypothesis justification. I think as well Francesca was talking about it a bit, absence of supporting information to support this hypothesis, and inconsistencies in the toxicological profiles. So those were the most common deficiencies for read across. And for grouping, which I agree with Francesca that it is more general approach, there are some additional deficiencies. And first is, of course, definition of boundaries of this group, and lack of criteria on which basis the substances have been included or excluded from the group. Low data density, so sometimes there are huge groups with not so much experimental data. And again, inconsistency in background data. So basically, it's very hard to believe that that basically this group is consistent toxicologically. And we did as well. We've been doing many seminars and trainings on read across with sharing the case studies, and we did this with our member states. And those observations which we have are quite consistent with the feedback which we get from them. Because if we ask them what are the two most common deficiencies in grouping and read across approaches, in respective of the process, we got those kind of answers. So as you can see, again, there is very little information to support the hypothesis. Of course, sometimes we have problem with substance ID, but as experimental evidence contradicts the hypothesis, there is no structural similarity. So basically, that was broader image and broader feedback from our member states on their experience in assessing the various read acrosses. And why it is then? Because very often, if you're opening the dossier, you have a hypothesis which directly lead us to predicted properties and the regulatory outcome, which in majority of cases is my substance is innocent, is basically negative. And hypothesis, especially at the beginning, in majority of cases was my substance is very similar to substance X. The substance X is known to be non-toxic for century, so my substance is non-toxic as well. That was more or less the hypothesis in the nutshell. While we know, and I probably all of us, we could find those examples. Of course, structural similarity is a good starting point because it's narrowing down a bit the possibilities of differences in the toxicodynamic and toxicokinetic profile. But we are all aware of the situation where very tiny structural differences lead to big differences in toxicological profiles. Here I have some example from the old papers, but I think everyone could make probably many of those examples. So that's why we know that structural similarity on its own is not enough. And so basically what we are as well trying to pass as a message that just having hypothesis, even if it is the best one, it is not enough. Hypothesis needs to be supported by justification and experimental evidence. And this is basically the majority of our dossiers is lacking. And this is where I believe, or we believe, that omics and molecular data in general and omics in particular can be really helpful. Because we are getting quite broad set of responses from our biological model, we can, with these data-rich responses, we can really substantiate our hypothesis better, and we have more chances to build successful and well-justified hypotheses. And we realized, so basically, once we realized this in our key area of regulatory challenge, the report which started in 2003, and now it's every year it's updated. Next year we'll have another update. I think since the beginning we had the chapter under shift away from animal testing. We have a chapter on read across and NAMs. So basically, if you can have a look at the report and read more why we believe NAMs and especially omics are really good idea to combine with grouping and read across. So just to conclude, we believe that it is essential to establish reliable methods for producing supporting evidence for grouping and read across. Omics, due to its extensive coverage of biological diversity, seems to be a very good form of evidence for the grouping hypothesis. However, we have to remember, and I think some of the speakers after me will try to walk you through, that the good omics data starts well before you are starting working on your read across hypothesis. We have to keep in mind factors like suitability of the biological model. So which model we are using to generate our omics data? Can this model exhibit all toxicological space which we are trying to use for our read across? Are we able to sample generate the samples in the consistent manner? What about sequencing? What about pre-processing? So all those factors will affect as well our robustness of our read across hypothesis if we want to use omics data. And so therefore, we believe that creating a consistent, transparent, and standardized methodology is necessary, especially in the context of omics, where you have so many different variables, you have so many ways to generate the data, interpret the data, and that we need to have a framework which will try to guide us through. And I think my colleagues, which will talk after me, will try to propose some elements of such a framework. And with that, I would like to thank you, and I'm happy to take a few questions. Unfortunately, I cannot stay with you all the time because I have to join. I just escaped from another meeting, and I promise that I will come back. But I'm happy to take a few questions now.
Thank you, Tomasz. I don't see any question in the chat, so you
Okay.
can.
Yeah.
I can maybe leave 1 minute for 10 seconds if they are, so they can go write something. No. So I think you can run away from here.
Okay. So thank you very much, and have a great continuation of the webinar.
Thank you, Tomasz.
Thank you. Bye.
Bye-bye. All right, Mark, I'm happy to introduce you for this next presentation. Mark's background is in the development and application of the metabolomics technology in regulatory toxicology. Mark is the CEO of Mishabo Health Science, which he co-founded in 2018 together with John Colburn. Mark, the floor is yours.
Which version can you see?
I see.
Is it changing to the?
It's in presenter mode.
It is in presenter mode. Okay, good. Thank you, Francois.
No, we see your next slide.
Oh, you okay? And I need to go here. It's in that.
Yes, perfect.
Good. Okay, that switched slides for me. I'm going to slide my camera. Good, thank you, and a warm welcome from me to the to all of you to give up a couple of hours of your afternoon or morning or evening to hopefully learn a little bit more about the use of omics, the grouping. So a clarification, that Francois is absolutely correct. One of my hats that I wear is I lead a small team in a business called Mashaba Health Science. I'm also a professor at the University of Birmingham. You will see the two logos in the bottom left and the bottom right. And I've used the logos depending on what case studies we're talking about. Some of this has been working with my University of Birmingham team, and other parts have been with the Mashabo team. But actually, the most important part of this slide is to say thank you to the European Union, because it's through the PrecisionTox grant that Francois mentioned at the beginning of the webinar that we're able to host and put on today's 2-hour event. So thanks to the PrecisionTox team. And actually, before I go into the science, one other clarification. Some of the work that I'm going to be presenting in this particular talk, it's relevant to some work at the OECD and ongoing work at the OECD called the Chemical Grouping Application Reporting Module. And I lead that as a representative of the UK, in no way associated with Mashaba Health Science. That particular OECD work is in draft form at the moment, so we can't discuss and present today. But the OECD has cleared me to say that work will be publicly available shortly. I believe it should be declassified in 2026. I do come back to this right at the end of my talk on one bullet point, and I'll show you how that piece of new OECD work that's still under development, how that fits into the bigger landscape of recent OECD documents. Right, into the science. And I'm going to just position you very quickly with a single slide. And it's the central dogma of molecular biology. Just to remember what we're going to be talking about here, we're doing molecular level analyses. And here we have a slide showing the flow of information from the genome through to what we call the metabolome, the endogenous metabolites and lipids, small molecule biochemicals. And for each of these 4 fundamental different classes of biochemicals, there's a corresponding ohm and a corresponding omics technology. And so I'm going to be talking, predominantly about metabolomics, and I've devoted the last 25 years of my scientific career to developing and applying metabolomics in toxicology. Let me just see if I can get a better pointer. And actually also use transcriptomics approaches, and Anthony's going to speak after me and talk in more detail about using transcriptomics for grouping. So this is the sort of the positioning to remind you of what we're going to be talking about. And just as a very sort of cartoon level introduction to how we use omics for grouping. So on the left-hand side, if you imagine some exposure experiments being conducted and you have a set of biological samples produced and you exposed to some number of chemicals. With the metabolomics, we're using mass spectrometry approaches to measure metabolites, measure lipids, and we're measuring the responses, of course, test system to the chemicals. And we call that biological activity, which we shorten to bioactivity. And the word bioactivity is used repeatedly through these slides. Because once we've measured using omics the bioactivity of the test system in vitro, it could be in vivo, we then go in and we start asking the question, well, how similar were the responses to 2 different chemicals? And you can conceptually think of this as something like fingerprint matching, where if you imagine that the omics is encoded in that fingerprint, and here's omics data encoded in a different fingerprint, you're asking the question, how similar are these? And we call that bioactivity similarity. So in grouping, whether it's grouping for whatever purpose, it could be for grouping read across. Of course, we have many different measures of similarity, and bioactivity similarity is the terminology we use for describing how similar the omics data is. Now, that's if you have two chemicals, but what happens if you have more? It gets more and more complicated. So it's really important in omics and omics data analysis that we have visualization tools. And one tool that we use is multivariate statistics. This is showing something called a dendrogram. And I will explain a dendrogram to you in a few slides' time so that you, if you are unfamiliar with them, hopefully you will soon be sufficiently familiar to interpret the results that I show later on in the slides. Now, I cannot give a presentation on the use of metabolomics for grouping and grouping read across without mentioning some very good colleagues at BASF and BASF Metabolome Solutions, who for more than 10 years, more than 15 years, have been conducting research in this area, pioneering research in this area. So I include people like Ben van Ravensway, Henneke Kamp, but several others in their teams as well. So if you want some good reading material, there's a lot of excellent publications from the BASF team. Now, what's evolved through their work, through our work with Acker in particular, is a 5-step workflow for how we apply omics for chemical grouping. And what I'm going to do through the whole of my presentation is keep referring back to this 5-step workflow. So as Tomasz was introducing, how we design experiments and the rationale for those experiments is absolutely critical. Then we generate some omics data and input data for the actual grouping. Third step is statistical analysis, this idea of comparing patterns and scoring and measuring how similar different omics responses are. Fourth arrow, toxicological interpretation, which is particularly relevant to Europe, not necessarily relevant in all jurisdictions. And then we pull together that information into the grouping hypothesis. And what I'm going to do in the next series of slides, they're quite text heavy as I walk you through, and I want to introduce you in more detail to the first 3 arrows. Then I will go and actually show you some results from the case studies, and then I'll come back to the 4th and 5th arrows later on in the talk. So let's start on the first arrow, experimental design and rationale. What do we mean by that? What are some of the considerations? And I mean, Tomasz has already said it. The selection of the biological test system is extremely important. So is the choice of omics assay and, of course, the choice of chemicals. When I talk about the chemicals, and on the next slide, I'll explain this in more detail, effect anchors are really very helpful and important in grouping in grouping. Digging into that a little bit more detail, what do we mean? Well, if this was grouping for the purposes of read across and reading across of a particular endpoint, when you're thinking about what choice of test system should you use, and then with a test system, what sort of sample type would you be using from that test system? That should be capable of exhibiting molecular changes that are either directly associated with the endpoint of interest or associated with a mode of action that is known to underpin and manifest in the endpoint. And what about the omics assays? Well, we want to be able to measure these molecular responses. So they've got to be capable of at least of measuring some of the anticipated molecular responses. And there's more detail behind these sorts of rationale statements, but I wanted to give you a flavor for what we mean by the design rationale. So effect anchors, what do we mean by that? A chemical that causes a relatively well-defined and characteristic molecular effect. Easier to think of if you're thinking of pharmaceuticals and biocides. And the effect anchors that you choose for a study, you can think of them as in-group or out-group effect anchors, and that depends whether or not you're hypothesizing they have a similar or different molecular effect or mode of action to the source and target chemicals in your study. The whole purpose of effect anchors is to increase the interpretability of a study, and you'll see how we can do that, and just to increase the level of confidence in the conclusions from the study. It is important to note, though, it's very easy to talk about effect anchors, but in the context of in vivo work, because of the ethics, it's probably not possible to introduce and use effect anchors. So this is more forward-looking. We're thinking about NAMs, we're thinking about in vitro test systems, alternative test systems for which we don't have the ethical constraints of in vivo work. And their effect anchors really are very important. But let me show you another cartoon. This is purely made up, but just to illustrate, one, to give you a bit more background on what the visualization of the grouping can look like, but specifically to show you how we can use and think about the use of effect anchors. So this is a cartoon grouping of 8 chemicals, and it's depicted in dendrogram. What you'll notice is there's sort of 8 of these what are called terminal branches, and each of these represents a chemical. And the axis across the bottom is increasing dissimilarity. In other words, if you are at this end of the scale near 0, you are high similarity. And when you look across the dendrogram, what you'll see is up here, you have 2 chemicals that are really grouped quite closely together because they're their omics responses are very similar. These 2 are very similar to themselves, to each other. And these 2 down here are quite similar as well. So that's the way that you interpret these dendrograms, by looking at the branch lengths. And then if we step back and say, right, well, with that knowledge in mind, where's the target? If this was a real set of results for 8 substances, where's the target? Well, it's sitting in this group, this sort of green group. It's sitting quite close to a couple of other potential sources. And we included in this test design some in-group effect anchors. And let's just pretend that mode of action 1 is the mode of action that these anchor chemicals predominantly act by. You can hopefully see some logic. Depending on how this grouping is done, and there's some subtleties that I'll come to a bit later, you can see the argument for inferring that the target substance may well act via mode of action 1 because it's sitting within the same molecularly similar group. And then you've got some outgroups down here that are acting via different molecular effects. Back to the arrows and more heavy text. Just to say something about the omics data and then what we call the input data. So omics data is made up of features, genes, metabolites, proteins, depending on what you're measuring. And then there are 2 key types of omics data that I want to refer to: omics profile data and omics signatures. And these are very different, and it's an important distinction. An omics profile doesn't contain toxicological knowledge from an a priori perspective. So one of the reasons we use omics is it gives us that broad, unbiased global analysis. So it measures an awful lot of the biological response. We want to retain that in the grouping and consider this large number of features when we do the grouping analysis. So the benefit of using something like the omics profile is we're using this extensive information, but it doesn't include external toxicological knowledge. That's to be contrasted with omics signatures, and some teams refer to this as omics biomarkers. So if you're happy with that terminology, that's good. So omics signatures or omics biomarkers comprising a pre-specified reduced set of features, and the key bit here is the blue text, that include external toxicological knowledge. So you can have a fairly small number of genes, say, or proteins or metabolites, which are specific to a particular toxicological effect, maybe specific to a mode of action. So the signature includes toxicological knowledge. The omics profile is not including in toxicological knowledge a priori. I'll carry that into the next slide. But before we move on, there's a lot of data analysis embedded in these 5 arrows that's way beyond my 40-minute presentation. I'll mention one important step when we convert omics data to input data prior to doing the statistical analyses. There's a process that we call bioactivity thresholding, and that basically says, do you have enough bioactivity in your treatment group to actually go forward for grouping? Because if the chemical has been dosed or the exposure concentration is too low and there's minimal or no molecular perturbation, of course, you can't group on that. You need to have an omics response if you're going to group. So we use bioactivity thresholding to remove very low responding treatment groups, which otherwise become reduce the confidence in the grouping analyses. So that's a little bit about the omics data and the input data. Then we go forward to the third box. Don't worry, we're 2 slides away from some case studies. We measure bioactivity similarity in this third box. So what is that? This is where the stats comes in. Statistical analysis to determine the similarity in the omics feature abundances. And you can group in 2 different ways, using profiles and using signatures. And I just, in the previous slide, began to introduce why we would use profile for grouping. We're retaining that really rich, extensive omics data, which has measured a wide swathe of biochemical response. So it's very, very good for a sort of a holistic initial view. The challenge comes if you do a grouping analysis with profile data, and imagine your chemicals fell into 2 different groups. To understand the basis for those groups and not have it as a black box, you would have to dig in and dig into the omics data to conduct further analyses to try and interpret those changes, which is challenging, doable, but challenging. The alternative approach is to use signatures, and the signature would be specific to an effect or a mode of action. And in that case, when you do the grouping, if again you had 2 groups reduced in the grouping analysis, if that grouping is based upon a signature, the interpretation of that result and the confidence that you get in that result is much more readily apparent. And at the back end of the talk, I will show you an example where we apply profile grouping and then we go on to apply signature-based grouping as well. So both approaches are very valuable. Pros and cons to both, but both very valuable, and we absolutely promote the use of both. The last couple of bullet points before I go into the case studies, how do we actually assess this similarity? Well, I've already mentioned the importance of visualization tools, but visualization tools we have to use very carefully because they can be subjective. And what we don't want is subjectivity entering the scientific field where we need to have robustness. So we need to layer in and make sure that we have appropriate statistical confidence in our visualization, in our clustering approaches. And third bullet point, and I'll come to this. Actually, this point is at the back end of the talk as well. Can we have objective measures of similarity? So we know that if we do structure-based grouping, you'll be familiar with the Tanimoto coefficient, which is a numerical value between 0 and 1 that measures structural similarity. Can we have something similar for omics-based bioactivity similarity? And the answer to that is yes, and I'll show you that later on. So let's illustrate this with some case studies. I don't have time, and I won't be going into these obviously in any sort of depth. All 3 of them are published, so I've put the papers on all 3 so you can dig into them in more detail. And they're presented, and I present them here in chronological order. And there's been a learning experience actually through the 3 different studies. The first is studying azo dyes. It's actually multi-omics, and this was our first piece of work with Tom Ash and team at EFA, applying omics for grouping. That works in Daphne Magna. The second study, which is also in Daphne, is also multi-omics. It's work with Jeff Hodges and Bruno Campos at Unilever. And that was a study where we investigated phthalates and couplers. And then the third study is quite different. It was this blinded ring trial. I'll explain it in a minute. And it's obviously already been mentioned earlier on in the first presentation. So this work was funded by the CEPIC LRI program. So let me talk through those 3 case studies. And key point, I'm going to go up to and no further than the bioactivity similarity assessment when I first present these 3 studies. So the azo dye study with ACCA, the context is this. We have a target, we have possible sources, and we want to select from 6 possible sources the most appropriate analog. So we're going to do analog grouping for in this case, read across. The target, dispersed yellow 3, 6 potential analogs shown here on the right-hand side. As I said, it's an exposure study was conducted in Daphnia magna, and we exposed the Daphnia to 3 concentrations of each of the 7 chemicals. So there's a total of 21 treatment groups. And I'm saying 21 treatment groups to prepare you, because on the next slide, there's a dendrogram. There's the results of the study, and it's got 21 different treatment groups. And when you first look at it, it's a little overwhelming in terms of the information that's here. But if you think back to the sort of the cartoon representation, then this is hopefully going to make a lot of sense to you. 21 treatment groups are shown on the right-hand side, chemical concentration pairs. Bioactivity measured across the bottom, increasing dissimilarity to the left. So if you look at the entire data set, the 3 omics responses that grouped most similarly, or that were most similar and therefore grouped closely, Sudan red G, low, medium, high dose. Very high, very consistent omics responses to those 3. In fact, if you look through the data, you'll see low, medium, and high for all 7 test chemicals. They group within each of the chemicals, as you may anticipate. So within chemical effects are more similar omics responses than between chemical effects. Now we're layering on some statistical confidence. So this 100 is 100%. It's from an approach called bootstrap resampling. And what that means is that we've run this analysis 10,000 times, and all 10,000 times that the analysis was conducted, these 3 groups, treatment groups, clustered together. So high statistical confidence in this particular clustering. Key question, because I don't have time to labor this slide, where's our target? Target sitting here, low, medium, and high are similar, 96% confidence in these 3 treatment groups. What is the nearest neighbor, if you will, to the target? It's Sudan 1. Sudan 1, based upon omics responses, illustrates the most consistent and similar response to the target. So coming down here, we then read across the Daphnia chronic tox to disperse yellow 3. And because we did the experiment in Daphnia, we went back into the lab, actually measured the Daphnia chronic tox in this with disperse yellow 3, and had a very high similarity to the value for Sudan 1. In effect, obviously adding a lot of confidence to this particular group. This was published in Archives of Tox. It was last year. Move on to the second case study. All the information on this case study is composed in one slide so that we can do the comparison of the key data sets. So this is the study that we did with Jeff and Bruno at Unilever and some of their colleagues, and importantly, Mark Cronin as well from Liverpool John Moores University. So we studied 3 phthalates, they're shown here, 3 uncouplers shown underneath. And what we wanted to do here was look at the more traditional approaches of certainly using structure as a basis for similarity assessment, and look at a wide range of different QSAR profilers. And this, of course, was Mark Cronin's expertise and contribution, as well as the Unilever team. So that's the middle piece. And then on the far right, and we'll come to that in a moment, that's the grouping based on omics. Structure-wise, no surprise, the phthalates are quite similar. Again, using the dendrogram representation with the 3 uncouplers, was certainly FCCP and CCCP very similar. The tetrachlorophenol, we can see from here, the structure is somewhat different, and you can see that in the branch links. When we looked at the QSAR profilers, while the phthalates fairly consistently grouped into 3, or the 3 phthalates grouped into one group across multiple different profilers, this wasn't the case for the uncouplers, which were far harder to actually group, and let's say correctly, as a group of 3 uncouplers. So in fact, none of the approaches that we used managed to generate the same color across all 3. How does that compare to the omics? Well, we can go and look on the right-hand side, and the first thing that you will notice in the omics is it doesn't look complete. And it isn't complete because we lost the CCCP group because the bioactivity was too low and actually failed to pass the threshold in order to actually have a meaningful omics response to be included in the grouping. So omics-based grouping, it certainly, it comes with its challenges. We would have needed to have gone back, rerun the dose range finding, rerun the exposure, generate the new omics data, and so on, and that just wasn't feasible in the timeline of this particular project. So we proceeded with 5 chemicals, and you can see with the 5 that at an omics response level, again, we have a grouping of the 3 phthalates and the 2 remaining unpopulars, and the confidence levels are shy. So that was published actually this year in Regulatory Tox and Pharmacology. So knowledge, certainly all the co-authors on that nice piece of work. And then into the third case study. I want to show the original Cepheid matching briefly. I'm absolutely sure that a number of you will be familiar with this, so I'll do this as quickly as I can. But there's an interesting twist, if you will, on this data set. We managed to squeeze more life out of it in a couple of different ways. So I'm excited just to say a few words about that. Matching stands for the metabolomics ring trial for chemical grouping. The aim originated from discussions, including with Acker, to say, can we test the reliability of using metabolomics chemical grouping? And how can we achieve that? And to achieve that, we needed to have a blinded study. And we ended up conducting an international ring trial. We had 6 metabolomics labs. And if we pop over here to the right-hand side, you can see the 6 labs, BASF, Imperial, Syngenta, and Free University in Amsterdam, as well as my team in Birmingham. And what happened was there was one rodent study conducted at BASF, generating plasma, and then that plasma was aliquoted and distributed to the 6 metabolomics labs. Those metabolomics labs, including myself and the team here, we did not know obviously the chemical identities. We didn't know the modes of actions that were being considered. We did not know how many groups of chemicals. We just knew that there were a total of 8 chemicals in the study. So it could have been that there were 2 groups of 4 chemicals and 4 chemicals, or there could have been 4 groups of 2 chemicals, 2 and 2 and 2. And we just had no idea what the makeup, what the grouping of the 8 really was. Each of the labs could then generate their own data. They extracted using the protocols. They generated their LCMS data, processed it using their own protocols, grouped it using their own protocols. When they had done the grouping, they then submitted it to Acker, which was contributing as an independent advisor on the project, and they also helped out on the chemical selection and also on the blinding aspect. So all the reports were sent to Acker, and when all the reports were at Acker, there was a blinding. Papers published last year, and in that unblinding, sorry, I'm going to skip through this one just to stay on time. This was showing different types of analyses that different partners conducted. And while it may look like there's different types of analyses and there are bases of those analyses, it's different types of multivariate statistics. But the key part is shown here on the left-hand side, that there was high consistency in those results. So there were 6 partners in total, but 1 partner pulled out because the technical quality of their data did not meet their own thresholds. Just as an aside, we will need quality control thresholds for the community at some point. So the partners assessed their own data quality and proceeded to grouping if they felt their data quality was sufficiently high. And for those 5 partners that proceeded to the grouping, they all obtained the same grouping pattern. So partner 1 through 5, they said test substances 3 and 4 are going to be in one group, 1, 7, 9 in another, and 2, 5, and 8 in another group. When this was unblinded, and we then knew what chemicals were and their modes of action, we didn't only confirm the high reproducibility seen on the left, we confirmed the high accuracy shown on the right. So by that, Group A, these are two androgen receptor agonists. Group B is the PPAR agonists, and Group C are inducers of anemia. So on the unblinding, this pattern that I'm showing you on the left, this consistent grouping was interpreted, could be interpreted in full. That is what went into the paper that was published that I showed you on the last slide. As I walk forward in these arrows and then move into the plausible toxicological interpretation, I can say a little bit more about the matching study. But first of all, what do I mean by and why do we need the plausible toxicological interpretation? To improve the confidence. This is not a black box game. We can't just have omics profiles being grouped. We need to understand what those underlying molecular perturbations are. So the plausible toxicological interpretation is required to associate changes in the omics responses with some form of effect, mode of action, diversity. The Cefic LRI program were very kind to be able to extend the initial matching study, and it has allowed the matching team to dig into the molecular analyses. And there's two quick bullet points I'm going to share. I can't show at this point all the results from this. It's sitting in an unpublished manuscript. We're just doing some final internal reviewing. There's another meeting in a couple of days, this Friday, to look at one final part of it, but I'd like to give you a couple of encouraging headlines. This extension of the work has confirmed that all partners have discovered statistically significantly consistent metabolic perturbations. We haven't discovered exactly the same perturbations, exactly the same metabolic changes, but statistically significantly consistent. And then from some really amazing work done by Annika Kende at Syngenta and Volker Haig at BASF Metabolism Solutions, integrating toxicological knowledge with some data from the matching study, we've managed to move into and achieve what we regard as a plausible toxicological interpretation. So I'm not showing you that here. I wouldn't have time in any case, because I want to show you another piece of work that is along the same lines, and I can demonstrate something about giving an example of plausible toxicological interpretation, or working towards this from some work that we've been doing with Tomasz and team. And what we did was, we said, well, we've got the matching data set, and now it's being unblinded and we know what the test substances are. Let's repurpose it, and let's make up the scenario and put it into a proper grouping read-across scenario. Now, this would be in the context of a positive read-across. So we have reformulated the problem, if you want me to put it like that, and said, okay, aniline is going to be our source for anemia. And this actually makes some sense, because aniline really does have a RE1 for blood system harmonized classification, so quite justifiable. We'll make 2-chloroaniline our target, and 4-chloro-3-nitroaniline will make the in-group effect anchor, which is pushing it a little bit because it's only RE2. The organ system is not specified. So not a perfect experimental design, but given we didn't choose the chemicals in the first place, we sort of reverse engineered a good grouping read across, reasonable grouping read across design here, with the other 5 chemicals serving as outgroup anchors. You apply bioactivity profile-based grouping. Okay, so no toxicological knowledge in this, and you get the dendrogram on the right-hand side. You knew this was going to group well because you've already seen this, that it grouped well in a few slides ago in the matching study. But this shows that source, target, and in-group anchor do group really nicely. Look at the red values. These are the appropriate measures of confidence. And when you look across this, you only see one deviation from 100%, and that's here where we have 99%. So the confidence in this grouping pattern is extremely high. But if this really was a dossier submission to the regulator, this is black box because we haven't said what is the molecular basis to this grouping. We're showing it just at the level of a statistical analysis, a visualization tool with statistical confidence layered on the top. Can we do something different? And this is where I want to show you how we can use metabolomics signatures for grouping. So we derived what we call a candidate metabolomic signature for anemia. We're not promoting this and suggesting that this signature is used by others as a signature for anemia. This was, I mean, you could if you wish, but here we've derived it for the purposes of the grouping study of the matching data. This draft signature or candidate signature has 27 metabolites lipids in it. For transparency, they're listed here on the right-hand side, shown in the graphical representation here. This is a form of network showing their associations to things like apoptosis of blood cells and anemia. Where do we get this information from? Some of it is experimentally derived, but some of it's from MTOX 700+, which is quite a useful resource, which was also work we did in my teams, but supported by co-authored by Eckhard Tomasz in this case, published a few years ago. And what MTOX 700+ lists, Eleanor went off into the public, any type of databases and journal publications that were publicly available, and gathered all information on metabolite effect associations, including looking at AOP Wiki, of course. And this paper pulls together and assimilates all that information. And in this portion of the paper, there's 722 metabolites, which is why they put it 700+. So we use this as part of the basis for deriving this candidate signature for anemia. Then we've taken that candidate signature for anemia and used that for the grouping. And this is what I show you on the next slide. So now we're doing bioactivity signature-based grouping. Here's the dendrogram. And don't worry about the fact that it's flipped around. That's completely irrelevant. Here's the target, source, the in-group anchor. I didn't say it, by the way. I've got to say it. Aniline low dose fails bioactivity thresholding. So that's why you only see a single dose for aniline. So here's your source, your target, and in-group anchors. Sufficiently high confidence. Look at the red values again. Over here, you've got all your outgroup anchors, very, very separate. Now, in this case, the interpretation of this result is almost straightforward. This grouping pattern is based upon 27 metabolites and lipids known to be associated with anemia. This grouping pattern very strongly links to anemia, and we can infer through the sort of guilt by association, if our source aniline is RE1 and our in-group anchor has a harmonized classification, and there's rigorous evidence to say that this is a group, you can imagine being able to read across a harmonized classification. They're positive read across. I said at the beginning or earlier on in the slides, we can also have objective measures of similarity. And this is where I want to show the objective measures of similarity very briefly. So objective measures of bioactivity similarity, we use cosine similarity scores. The ASF uses something very similar to this, very slightly different, but similar enough that I'm going to regard it as equivalent. And through BASF's work and through our initial work, the similarity score, which can be a maximum of 1, which means perfectly identical. 0.5 seems to be around the threshold for that, how similar is similar enough question that we all talked about for many years and wondered about. So a value above about 0.5, and you're into it's similar enough to be called a group, value below that, and you would not be regarding them in the same group. Source target in-group effect anchor. Here you are. There's the evidence of above 0.5. That's referring, of course, to the group on the left. And then all the out group compared to the target, these are the values here, and they have a low similarity. So Those are objective measures of similarity. Cosine similarity scores actually go from +1 to -1, but that's a little bit of detail. The point is we can now use this objective measure of similarity as well to add even further confidence in terms of which substances we are putting into groups. Now, I think I have about 1 or 2 minutes left, and that is just about long enough. The final arrow, all I have to say here is the final arrow is in effect looking at stats from the third arrow and the Tox interpretation from the fourth arrow. Bring that together and you can form the grouping hypothesis. And that will be it to the 5 arrows. There's a lot more to it, of course. There's a lot of detail and depth. Just as I introduced at the very beginning that this particular 2-hour webinar is supported by the PrecisionTox and the European Union funding, we also have in PrecisionTox funding to support some one-day training courses on this very topic. So if any industry or regulatory consortium are interested in having a one-day training course that goes into the last 35 minutes in obviously much more detail, please contact me. It's fully supported through PrecisionTox, so we're able to provide that. Another sort of shout out for a relevant paper is this utilizing Omics data for chemical grouping that a number of organizations published last year. A good introductory read. I want to talk about briefly 2 really important OECD guidance documents that sit really beautifully next to each other. And the timing here is so fortunate because the first one that I'm going to mention was literally published or declassified just a few weeks ago. So on the 30th of October of this year, the long-awaited update on the guidance and grouping of chemicals has been declassified and published. So it used to be called Guidance Document 194, which was the 2nd edition. And after, I think, a few years of work, 418 has just been published. It's over 250 pages, but if you want to learn about guidance on grouping, this is the one-stop shop, an extremely valuable document. And it has information on Omics and on reporting. So very relevant to today's presentation. The other document that sits very much alongside the one I just mentioned and it's cross-referenced, this was declassified a couple of years ago, and I'm sure you've heard of it, the ORF, the OECD Omics Reporting Framework, and that is a detailed guidance on how you would report Omics data in a lab-based TOPS study, as it says in the title. And on my second slide, I said there's an ongoing piece of work in the OECD developing what's called the Chemical Grouping Application Reporting Module. And that module is an extension of the existing modules here in Guidance Document 390. So it's a watch this space for that. Last slide, just to wrap up, and I'm sorry, Francois, I'm doing my usual minute or 2 over. Basically, there's an awful lot of effort that's gone in from many, many different teams over the last 5, 6, 7 years, and BASF's work, even longer back than that, contributing to where we are today. And where are we today? We have reliable workflows for using Omics for grouping. They're there, they've been talked about, they've been published. We've got lots of case studies, not just us, not just BASF and BMS. Other groups have been publishing on this topic as well. So there's a good body of scientific evidence there. Now we need to start really putting it into the regulatory, testing it in the regulatory paradigm, as opposed to more basic research case studies. I didn't say this, but I just want to shout out about this one point. We really need to have concerted efforts towards developing, initially prioritized, but developing Omics signatures and Omics biomarkers, getting these into the public domain so that we can move forward the Omics, not just in grouping, but more widely as well for hazard ID. And since it's halfway through December and we're sort of thinking about winding down soon, I thought I should say something about 2026 and things to look forward to. I've already mentioned matching. The second paper from the matching study should be published in 2026. So That focuses on plausible tox interpretation. And something else, we're really keen on getting all these methodologies that we've been working on with others out into the public domain and as fully and widely used as possible. So there's a paper being written up that actually will describe in much more detail about these grouping workflows that we're using and how to use them with case studies and so forth. So watch this space in 2026 for that. Thank all the colleagues, amazing colleagues across so many different organizations. Sorry for overrunning, Francois. Back to you.
No problem, Mark. It was worth listening a little longer. It was an impressive talk, and thank you for making omics and grouping a reality. It's nice to see the progress. We'll now go for a short break. Feel free to drop a questions to the panelists in the Q&A box. They are slowly coming. And we meet at 4:17 Brussels time. Thank you. All right. Waiting for Tom. Mark, I have a question from you by one of the participants.
Yes.
And you mentioned that they shoot you an email. So it's okay if I put it in the chat for all the participants?
Yeah, which one though? I guess they're
It's the Mishabo
yeah,
.co.uk. You can
yeah,
send
but
it. You can
can we
send.
can we do it later? Because
Yes.
I don't want to be appearing to be promoting.
Okay. Fine. You can think about it
I'll think
and
about it. Let me come back to it. Yeah.
exactly. Okay. All right. Our next speaker is Anthony. And Anthony is the exotic part. He is from Canada. So thank you for being with us. So Anthony is a scientific evaluator in the existing Substance Risk Assessment Bureau at Health Canada. He holds a PhD in medical science from the University of Alberta, specializing in toxicology and chemistry. Anthony completed his postdoctoral study at Health Canada before joining the Regulatory Bureau in 2021. Anthony, the floor is yours.
Okay, thank you. Just making sure you can see my screen there.
We see the slide deck.
Okay, I will put that in.
That's good.
Perfect. Okay. Well, thank you for that introduction, and thank you to Mark for covering all of those concepts with the grouping, because it gives me the opportunity to get into a little bit more detail about the case study itself. So the case study here used transcriptomic data as a basis to establish chemical groups. I'll be speaking not only about general gene expression profiles, so that's that profile-based grouping, but also the use of a biomarker for that signature-based grouping to provide a mechanistic anchoring for grouping similarities. So I'm sure many here are quite familiar with the concept of transcriptomics. To be very brief, essentially referring to the transcriptome, reflecting the active expression of genes. The advantage of high throughput transcriptomics is rapid data collection can be obtained from either in vitro models where you get concentrations, or short-term in vivo designs giving you doses, typically analyzed using either an RNA-seq or microarray platform. Within a risk assessment context, transcriptomics provides information on the level where these effects are occurring, so the potency of these chemicals, as well as provide some hazard information relating to specific genes that have a response as a result of the exposure. So for our purposes here, the output I'll be talking about that's used in this study were profiles of differentially expressed genes, which I'm going to be referring to as DEGs. So these are significantly changed at defined exposure concentrations when compared to the control for a given chemical. As for the case study itself, the aim here, of course, was to demonstrate the potential to group chemicals using similarities in bioactivity, represented by elicited changes in the transcriptome. So the objectives were to identify a fitting data set, so the one that shows changes in the gene expression with a particular underlying mechanism to focus on, consolidate and process this data. So this was done using an in-house bioinformatic pipeline, but it's based on published guidelines called the Omics Data Analysis Framework for Regulatory Application. So our ODAF that was published a few years ago, Health Canada has its own modification of this pipeline. A workflow was developed to assess the grouping of these substances based on similarities in bioactivity, so using those profile-based groupings, using all significant features, as well as the signature-based grouping. And then finally discuss some of the sources of uncertainty based on the techniques and as well as the data itself. Now, omics signatures, such as transcriptomic biomarkers, may be used to interpret mode of action or mechanistic properties. Here, an 81 gene transcriptomic biomarker was developed to detect histone deacetylase inhibition So this was done using human TK6 cells, so lymphoblast cells. The methods and the approaches that were used to develop this biomarker are available in some past publications, so I won't get into too much detail about those. But basically, we used a selection criteria to obtain a readily available data set. So this was developed and validated at Health Canada, so we had all the raw data available to us in the background, and the experts that had conducted this study. The chemicals within this data set were either specific to histone deacetylase inhibition, so I'll be calling those HDAC, to be compared with other non-HDAC chemicals with more diverse modes of action. Although the 81 gene biomarker was derived using the whole human transcriptome, so it's about 20,000 genes, it has been shown to be effective using smaller, more targeted templates, such as the S1500. So it's a versatile biomarker. As for the workflow, the data set involved, as I said, was TK6 cells. So this used 31 chemicals, 14 of which were HDAC specific, and 17 had non-HDAC modes of action. So as part of the previous work in biomarker development, these chemicals were externally screened for cell viability, HDAC enzyme activity, dose ranging finding experiments were performed previously to this transcriptomic study, and the HDAC signature derivation. So to make sure everything was working or giving the results that they were supposed to. So the data set was consolidated and imported in the form of raw data. So for those interested, these are FASTQ files that were produced using the TempoSeq platform. It was then processed using our ODAF bioinformatic pipeline. So applying QA/QC criteria to ensure the accuracy of this data, as well as to produce those differentially expressed genes. That was done using the DE-seq2 R package. So the input data was represented by the number of DEGs at each concentration, where an increase in the number of DEGs would represent an increase in bioactivity. To simplify the similarity analysis, that a bioactivity threshold was applied to remove low and non-active samples. And finally, the bioactivity similarity itself was done using a hierarchical clustering analysis, so producing those dendrograms that you saw earlier, as well as a principal component analysis as well. And as for the approaches, as previously mentioned, bioactivity-based grouping, so using all identified differentially expressed genes from each of those concentrations post-threshold, and the bioactivity signature-based grouping using reduced gene template, so focusing on those 81 genes that are HDAC specific. So here we have a list of chemicals with the available concentrations with their corresponding DEGs. These, I know there's a lot going on here. These are portrayed as a proportion of DEGs, differentially expressed genes, to the whole transcriptome. So that's where you get that sort of 0.1, 0.2 along the side axis. But essentially, more DEGs equals increased proportion of bioactivity. The threshold that was applied here was 0.01 or 1% of the overall gene template. This is represented by the red dashed line. And it was just as a minimum to have a measure of that bioactivity, filter out any of those inactive or very low active concentrations. So here, most of the chemicals surpassed the filter. From the 31 chemicals, we had 25 chemicals that were selected, and this allowed us to have that an optimal concentration that could be carried forward for that bioactivity similarity assessment. So the first outcome with bioactivity profile-based grouping using all DEGs, within the hierarchical cluster analysis, the HCA, a dendrogram of chemicals is grouped by biosimilarity. It's listed along there. The chemicals are all listed along the bottom of the axis. And then on the y-axis, you have that height, which is the dissimilarity that was spoken about earlier. And the analysis itself was done with the PVC clustering package in R with bootstrapping that produced confidence intervals and associated p-values. And this was, to get into a bit amount of detail, it was done with a Pearson correlation as a distance metric and average linkage. Within the PCA plot, principal components were computed using the PR comp function in R, and visualized using ggplot. So we have our non-HDAC chemicals that are portrayed in green, and then our HDAC-specific chemicals that are in red and blue. So there are actually two subclasses of HDAC chemicals within this. So as for the results, the HCA on the left, as I mentioned, we had those optimal concentrations. Some chemicals had multiple concentrations, so a low and a top dose were selected for those. And we have two main groups. All the non-HDAC chemicals were separated in, group 1 had only non-HDAC chemicals, so there's a smaller group there. Whereas group 2 had sort of a mixture of non-HDAC and HDAC chemicals. So from the bootstrapping within the clustering analysis, we got these confidence intervals that are portrayed with those rectangles. And so we have all those chemicals that are grouped together. However, if you look a little closer towards the middle, you will see that there is sort of a subgroup of chemicals that look like they're separated from or a little bit more similar compared to the others. And those are actually all of our HDAC chemicals themselves. So even though we have this whole group of a mix of these chemicals, there is a defined subgroup of HDAC within the center of them. And the PCA confirmed these results by showing sort of that they were not cleanly separate. There was some separation on PC1, but you did have that mixture of non-HDAC and HDAC chemicals that were mixed together. In essence, we have two groups, and the idea is if we know nothing about these chemicals, we could do a deep dive into the type and magnitude of those DEGs to draw conclusions. In this case, because we have the biomarker, we can refer to that and a defined set of genes in order to provide a more definitive conclusion. So here we have the bioactivity similarity, the signature analysis with gene expression profiles restricted to the biomarker genes using the same pre-selected concentrations. So the list of chemicals is indicated as well. We have, instead of those two groups, there are multiple groups with confidence intervals. However, I would draw your attention to the target grouping of that larger group of chemicals sort of on the right side. And that is those are all of our HDAC chemicals that were grouped together based on the biomarker. So we have these chemicals that are separated from the rest. And if you look closely, there is a branch toward the top there where 3 of the chemicals are separated from the others. And those are actually in red on the PCA plot. So those there are class 1 specific HDAC chemicals compared to the other ones, which are called pan HDAC chemicals, which are non-targeted. So the PCA plot on the other side did reinforce these results by showing the separation in those groups, noting that they do look a little bit more spread out. And this is actually because the axis is sort of zoomed in compared to the previous plot. So it looks like they're separated a little more, but actually they are grouped relatively close together. Though the HDAC, interestingly enough, the HDAC chemicals seem a little more spread out compared to those non-HDAC chemicals in green. So just to very quickly summarize, because I had given my short time frame, these gene expression profiles using DEGs at defined exposure levels allowed for the identification of chemical groups. So from the general grouping of chemicals using the bioactivity similarity assessment, the profile-based groups was not able to sort of cleanly separate HDAC from non-HDAC chemicals. So it does provide an indication that there is something else going on here, but an in-depth analysis would be needed because HDAC may not be the only mechanism that is driving the expression of those genes. So instead, a signature-based analysis using a biomarker of 81 genes provided an informed basis behind that grouping and a mechanistic anchor for these groups. But in general, as you can tell, there's a lot of we know a lot about these chemicals. So these approaches tend to favor lists of chemicals that have more toxicological information available. Though even with the profile-based grouping, you could do a deeper analysis of those chemicals themselves. So as for the uncertainty, I'll just put up all of them here. It's an overview of some of the major categories of uncertainty. Relevance to the methodologies. So this was with low uncertainty. This is because this is based on published methods with an established biomarker, and it was done under a defined set of conditions. So there was an informed basis for this grouping. We're confident about those. The reliability of the omics data itself was also low uncertainty because these were done the analysis and processing was done using standardized practices with an established pipeline to generate that transcriptomic data. The bioactivity similarity analysis was more low to moderate because we did have reproducible patterns, but the resultant groups were a little bit more open to interpretation. And finally, the plausible toxicological interpretation was also sort of low to moderate uncertainty. This is it's generally low, though, due to the knowledge of the biomarker and its validation in previous studies and the consistency of groupings between the concentrations producing DEGs. So we had that target grouping of HDAC chemicals that was reliably produced. And so overall, low to slightly moderate levels of uncertainty within this analysis give us a relatively high degree of confidence in the results that were produced. And this is my last slide, just talking about some of the conclusions. The approach does allow for transcriptomic data-driven analyses to reinforce current knowledge and provide insights into associations of even data-poor chemicals for read across. Using robust transcriptomic data lends confidence in the established groups. And these modules can actually be readily integrated into transcriptomic frameworks. So it was designed as a workflow that can be an ancillary analysis to other parts of a framework. There are some further considerations that were not in this particular study. I've done more benchmark concentration modeling. So rather than using single concentrations, to do that benchmark concentration modeling across a concentration response curve for a chemical would give us a much more detailed result. And the application of additional signature analyses. So what I mean by this is if we had multiple transcriptomic biomarkers on top of HDAC, there are lists of that we have available at Health Canada. These can be applied to larger groups or data sets to refine or identify specific groups based on their on a mechanistic anchor or mode of action. So with that, I would like to thank PrecisionTox for giving me a platform to speak today. And I would also like to thank all of the collaborators and contributors that were involved either indirectly or directly with this particular work, with all the biomarker work that was done, as well as my colleagues with the OECD. So I will leave it there, and I will open up the floor.
Thank you, Anthony. We'll finish now with the final presenter of today's webinar. It's Tom Lawson. He's a senior scientist at Mishabo Health Science with more than 10 years of experience in biological research, bioinformatics software development, and data analysis. He's now focusing on the utilization of omics data, particularly metabolomics, to support the assessment of chemicals. He holds a bachelor in biochemistry, a master of science in bioinformatics, and a PhD in computational metabolomics. Tom, the floor is yours.
Okay, thank you. Hopefully my connection's okay because I did lose it a second ago, so I'll just watch out for that. Okay. So I'm going to be talking about and sort of that added bonus of using metabolomics, where we can not just measure the bioactivity, which we've been talking about here, but we can also measure get information on the parent chemicals and the biotransformation products. So let's just jump in straight into it. So what am I talking about here? So in mass spectrometry based metabolomics, we just hide this. There is no intrinsic filter to separate out whether the ions are from an endogenous metabolite or lipids, or if those ions are from the exposure chemical and the biotransformation products of those exposure chemicals. So what that means is that when you measure a sample in an untargeted metabolomics experiment, you're measuring both the toxicodynamic response, i.e. the bioactivity of the endogenous metabolites, as well as the toxicokinetic measurements of the exposure chemical and getting information about the metabolism of that compound. So historically, this is almost seen as a negative thing. You might have a huge peak in your data set and you want to remove it because you don't want to be doing this huge peak maybe from your exposure chemical, and you don't want to be grouping on that. You want to be looking into your endogenous compounds. But over the past few years, many people have been trying to this information and seeing what could be useful and getting that information of these biotransformation products and the parent compound from the metabolomics in a more robust manner. So there's some papers here from Mark's group, but also papers from other labs which are doing something similar in different test systems and using different approaches. And what the outcome from this, one of the core results you can get from this is very rich insight into the metabolism of the exposure chemical, in these cases, a drug. So seeing it here on the left, in the middle, there's the drug, which is sunitinib, and you can see here there's been confirmation of various biotransformation products from the LCMS, and the same here again from this paper. And all of these approaches are sort of following a similar methodology. There's variations in it, but the very basic simplified version of it is where you have basically your exposure study, and you have your in the test system from either the Daphnia or rat or some cell line. Take those biological samples out, and then you measure on the LCMS system. So as I said, when you're measuring that biological sample, you're measuring both the endogenous metabolites and any of the parent compound and those biotransformation products, and that's all within that raw data. So the next step would be to do some data processing, and whereby you're processing all those features from that raw data. And the traditional approach, and what we've been talking about before, is you extract out those the endogenous features, and then you do your endogenous feature analysis. So this could be essentially the grouping analysis, which Mark and Anthony have been talking about. But additionally, you can extract out these what's called here xenobotic features by the parent compound and the biotransformation products of the parent compound, and you can also do analysis on those features. So also key to this, though, is the reason why there's been sort of increasing usage of this, one of the reasons anyway, is the much more use of fragmentation data. And what you can do for experiments is you can have sort of what's called a hybrid approach of both untargeted and targeted. So we can also, as when we collect this data, we can target certain features which can be we can get more MSMS data from, which helps us improve the annotation. So what do we do with this information? So if we measure the parent in our data set, we can get some classical sort of toxicokinetic parameters from this, so or at least near to those parameters, so we can measure how the parent is cleared if it bioaccumulates. And then also we can see if the parent chemical is metabolized. That's the pathways I showed before. And this is done at the same time as measuring the endogenous metabolic bioactivity. But key though is if we can measure this on multiple exposure chemicals, can we also do a form of grouping as well on this information? Can we actually group on the metabolic pathways which we've helped elucidate here? Similar to how we were grouping on the bioactivity. So what we call here, can we calculate an empirical metric basically between these pathways, and we call this metabolic similarity, and that's I guess to the bioactivity similarity here. So to address this sort of proposal, a case study was created with Unilever, Shabo, and University of Birmingham. And the idea was to use mass spectrometry-based metabolomics to study Daphne magna as an ecotox model and compare 3 phthalate compounds and 3 colonazole compounds. And the idea is, could we actually measure those parent chemicals in each Daphne extract, see if they bioaccumulate, did they clear, what was their response over time, and can we then discover BTPs and metabolic pathways, and ultimately could we group those phthalates and conazoles based on this metabolic similarity. So that here are the compounds chosen. So there was 3 phthalates and 3 conazoles. There was various reasons for the choice of them. But key consideration here, though, was that they both predicted metabolism, was observed. So we predicted the metabolism using a few tools, but predominantly one called Sigma, and that there was shared metabolism between these compounds, both the phthalates and conazoles. In addition, they wanted some level of evidence, either from our previous work, to show that they could potentially be metabolized in crustacean. So we had some knowledge prior for phthalates from the work actually, which Mark was showing earlier. And for conazoles, there was some prior evidence in shrimp that BTPs can be, I think it was for propiconazole. And there's also evidence for the azole, the triazole fungicides that the BTPs were actually were present across different species. So, but those are the chemicals chosen. And so the first step was then to look at, can we measure the parent chemicals in the experiment? So the experiment was set up for 3 exposure concentrations, low, medium, high, set up based on chosen based on a prior dose range finding, and then also using 2 time points, 24 hours and 48 hours. So first thing to note is that the parent compound of all the compound exposure chemicals was observed within all test conditions, and it was identified with a standard. So from this as well, you can then see that you have a nice dose response for the low, medium, high, and you can also see the differences between 24 hours and 48 hours. So there was no obvious substantial bioaccumulation or clearance. There was significance between 24 and 48 hour low dose, but there's not a substantial increase really. But so all we can just find from that basically that there's no major bioaccumulation or clearance. And then we went in to look at the BTPs, which we could measure. For the phthalates, we could measure quite considerably more than conazoles, but for both, there was phase 1 reactions observed and phase 2 reactions as well. So for each of those, then we could create these metabolic pathways. And I won't go through every single metabolic pathway, but here's an example for one of the phthalates. And what you have here in the middle is the parent compound, and here's that intensity plot, which was shown for the parent in the previous slides. But what you can also do is you can generate this for each of for some at least of the BTPs as well, and then you can see if the BTP response over time and dose is similar to the parent, if it's bioaccumulating, if there's clearance, etc. And generally speaking, though, this pattern was similar between the parents and the BTPs. Just a note of this as well. Often an exact structure isn't able to be annotated from the workflow. And that's why we have these R groups where it's not entirely sure where what the exact structure is. So for the phthalates, what was actually observed in terms of BTPs which were shared across these three compounds. So phthalic acid. So there's a lot of information on this particular figures table, but essentially it's showing there's four BTPs which were shared between at least two or more of the phthalates, with phthalic acid being found in all three. And in particular, we had some added confidence in a few of these. So if there was two ticks, it meant that the BTP was observed in essentially two independent daphnia chemical exposure studies, because we had a prior work in for the phthalates in daphnia, so it's been observed. We have more confidence in those, and also there's different levels of confidence in terms of the annotation of these, and in some cases we were able to further annotate it with the BTP with in silico fragmentation using a tool called METFrag. The picture is slightly different for the conozols, whereby there wasn't actually any identical structures which are observed for the BTPs which were shared across the three conozols. However, many of the reactions observed were the same. And again here, there was only two BTPs observed for these two conozols and only four here. But again, we get to see the intensity, how the intensity changes over time and dose for both the parent and for the BTPs. And again, often it was very similar, the pattern observed, not always. Okay, so we've measured these, we've elucidated these metabolic pathways for the different conozols and phthalates. So next step is want to see how similar these are. How can we determine how similar these metabolic pathways are? And this isn't this is something which has been looked at not just for metabolomics data. This is often a case where some may have predicted the metabolic pathways for multiple compounds, and they maybe want to choose the right the most similar analog for full grouping and read across. And there's different approaches have been already done for this. I've broadly broken down to a few here in terms of compound-based approaches. So that could be where you want to look at the similarity of the compounds within each pathway. So in that case, you could turn essentially the pathway into a presence-absence binary fingerprint of what compound is present. And similarly, you could do that for the reactions as well. You look into the reactions occurring for the biotransformation, and you can turn those into a fingerprint and look at the similarity between those fingerprints. Additionally, there's various other ways you can look at this incorporating different information, but there's these two approaches here, and of course there's also networks approaches, and increasingly being used for this type of analysis. However, for this case, we've just stick to compound-based and reaction-based fingerprint approaches of looking at the similarity, where we calculate a similarity distance matrix and then form some clustering. So hopefully this seems similar to what we've been talking about in terms of the bioactivity-based grouping, and similar type approaches used here in terms of trying to calculate that similarity. And the results of which is I'm showing here for both compound and reaction-based. So the first one here is basically we have the dendrograms which we've been seeing before, and these are the confidence replicability confidence here, so quite high. And what you can see is that the phthalates have grouped together, and two of the conozols have grouped together, but one of them hasn't. And this is because within those BTPs there is nothing which is past the threshold of similarity in terms of the compound within those pathways. However, if you go to more reaction-based grouping, you see that this similarity is a lot more clearer, and it groups the conozols and phthalates more clearly into those two groups. And if we look a bit more closely, you can see the highest similarity here is between the metabolic pathways between propiconazole and itaconazole, these two here. And I mean, this is maybe quite obvious why that would be the case, because the initial parent structure is very similar as well. So you would expect that. So in conclusion, this is a sort of an added bonus of metabolomics, which can be means that with the right data processing workflows, you can also measure parent chemicals and biotransformation products of those chemicals. You can then apply metabolic pathway-based grouping, and at least in our case, is able to confirm the test substances by their class. And we're hoping to publish this in early next year in terms of the case study. And we're also working on a perspective article where we want to show how this is an emerging field, how this is basically the opportunities involved here, and also some of the challenges, because I've glossed over some of the difficulties in doing this analysis and haven't really mentioned about anything in terms of the quantification of these BTPs and the challenges involved with that. So that's the last slide. So thank you for your time.
Thank you so much, Tom. We are slowly running out of time. I can only take a few questions that were submitted. I also recommend that we will send you also the responses by email from the panelists. For the people who put their name, we have your email. Maybe I can take the first one because we still have 5 minutes. So it depends how quick you answer, dear panelists. The first one is for Mark. You presented case study on the use of Daphnia and rats for omics-based grouping, but what are your thoughts on the use of other species like zebrafish, or even the use of omics down at the in vitro level? Obviously, it depends on the question you're trying to answer, but do you have any thoughts on the pros and cons of certain species, brackets in vivo, or cell lines, brackets in vitro, for omics-based grouping?
Okay, I would try and be super quick. I mean, the omics are absolutely applicable across in vivo, in vitro, and alternative test species. The key issue there is going to be choosing the right test species to make sure that if, for example, you are focused on grouping read across, then it was on one of the earlier slides in my presentation that that test system and the sample that you derive from that test system is capable of exhibiting at the molecular level the effects that you're interested in. But the technologies are widely applicable. And there's certainly work published on in vitro metabolomics and grouping. And as you said, they're absolutely applicable to zebrafish-based studies as well. And I'll stop right there just so that other speakers can get some questions and answers in as well. Thank you.
Yes, I will make a panache of the questions to address some of the panelists here. There is one for you also, or a few for you, Anthony, but I'll go with the first one who came. Anthony, could you share a bit of background on why TK6 was used? Be sure.
Yeah, to be very brief, the TK6 cell line was used in a previous study for another biomarker on genotoxicity. That's called TGX-DDI. And I believe the HDAC biomarker was built on top of the TGX-DDI biomarker. So it was just to use the same cell line. If I recall, I believe it was originally selected for TGX-DDI because of it readily detected perturbations, and also it had P53 activity, I think, for the two main factors. So I can post that paper. It's from back in 2015. So that's the short answer.
Okay, that was great. Maybe, yes, you can share this info to us and we will forward it to the participants. There is one that sums up you, Anthony and Mark. I will read it. So I think it's a follow-up question that the person was asking, but Thanks for the great webinars. Do the speaker have any idea which omics method works better in which case? Are there any studies on this? So you partially answered to it, Mark, in the previous question. And then there was another question saying, I would guess that for omics analysis, chemical reactivity is required to be able to see something. What about chelating agents that are only, and excuse my French, sequestering metal ion?
Well, the topic of the pros and cons of different omics approaches in toxicology and for omics-based grouping, I think requires a visit to the local pub in a few hours. There's clearly pros and cons. Almost all of the work that we conduct, we use multi-omics because we see value in downstream molecular measurements being measured by the metabolomics, arguably closer to adverse phenotype or downstream effect. But of course, the value of the transcriptomics and the specificity of the effects on gene expression is incredibly valuable as well. So if it's an affordable, because two omics, of course, is adding, going to add to the cost. If two omics are possible within a particular study design, that's the approach we've been using, and the whole PrecisionTox project, which is supporting this, as we said, supporting this webinar. This is a vast project over the last 5 years, looking at multiple test systems, but it's all multi-omics and all using metabolomics and transcriptomics.
That's true.
Can
Yes,
I pass on the second question because we've run out of time, and Anthony may want to respond.
Yes, Anthony.
That was on the sequestering. I hadn't thought about that aspect. I don't know if you had any thoughts, Mark.
The only comment would be if the toxicity is involving sequestering of metal ions, I mean, that there would need to be some downstream effect that ultimately leads to gene expression that would be detectable using transcriptomics or effects on proteins or metabolites, lipids. We're not going to have an omics response if it's a chelator binding to a metal. If that was the totality of the interaction, we would look at downstream effects.
Yeah, something that directly affects the process. So that makes sense. Thank you.
Okay, last questions. And then the rest will be answered by email. I have also some PrecisionTox partners sending questions, but Mark, I guess you can have a direct talk with colleague Stefan. Anthony, any thoughts on the data source for additional biomarker to expand the mechanistic hypothesis testing for grouping?
Yes, we have been consolidating a list. I think we have about 10 different lists of biomarker genes, and that should be published in the paper in the near future. So, and I think it's just that we've got some work on estrogen receptors, androgen receptors. There's a lot of work on genotoxicity biomarkers. Now, the only question is, have they been, only a few of them have actually been validated, so thoroughly tested. So there's a ton that we have been sort of testing out now, just to digress a little bit, the biomarker works, as Mark had emphasized, if you use that with the right experimental design. Like estrogen receptor biomarkers, they're going to work in, we use MCF7 cells, a breast cancer cell line. The TGX DDI and the genotoxicity is used in sort of a more of a liver-based model. So it is going to depend on your design, but yes, there is a list and there will be more available. So we're hoping to expand on that aspect.
This is the end. I'm sorry, guys, there are more coming up, but we gotta go. So as said, we'll take the questions and reply to each of them by the panelists. Thank you all for listening and staying with us for the last 2 hours. And we keep in touch. With this, I wish you a nice end of the day. Bye bye, everyone.
Thank you, everyone. Bye-bye.
Thank you.
Bye-bye.
Thank you.